fortunate today to have Colleen Duffy from mathematics, and she's going to talk about understanding algebras made from polyhedra and multidimensional polytopes. And by the time we finished conversing about that, I had a vague idea what that was all about. So.
Well, don't worry. My talk will begin with a bunch of definitions to understand all the words in the title. And then I'll do a very brief history of where this topic came from, and then the work that my students and I have been doing for the past several years on this topic. So I'm going to start with saying that we have for math talks. I'm not sure if it's also saying used in other departments or not. You can let me know. But the first 15 minutes of a talk, everybody understands. The next 15 minutes, the people in the field understand. The next 10 minutes, only the experts understand. And the next 5 minutes, only the presenter understands. And the last 5 minutes, nobody understands, not even the presenter. So we'll see where we get here. All right, so first, the definition of a polytope. So a polygon is just a two-dimensional shape. You know, a triangle, a square, octahedron, all of those. So then we can build up to higher dimensions. So a three-dimensional shape is a polyhedron. So that'd be like a pyramid or a cube or an icosahedron like I have pictured here. This one will come up later in the talk. And then we can build up to even higher dimensions, a four-dimensional object or a four-dimensional shape. So that'd be a polytope. So polytope is just sort of the generic anything more than three-dimensional now. And so here we have pictured the four-dimensional version of icosahedron. So this shape in 4 dimensions, well, the two-dimensional projection of it. So you can imagine it going off in some other direction we can't visualize. And this is the shape that my students and I are currently looking at and considering this semester. So we're going to be referring to the vertices, edges, 2D faces, the 3D faces of these objects. So the vertices, just the corners, the edges connecting the corners, and then a face would be like these triangular faces here. And then this four-dimensional, you can kind of see here, you see that pyramid type shape. So the faces of this four-dimensional icosahedron are really pyramids. And so those would be the three-dimensional faces, or sometimes referred to as cells. So if I say the word cells, it's because I forgot and I meant to say the word face for your sake. And so what we're really concerned about is with these objects are the symmetries of the object. And so we're going to be taking them and we're going to be, spinning them around, we're flipping them over. And what we really care about when we're doing these motions is, first of all, what are the symmetries of an object? So you're looking at that four-dimensional icosahedron. It's hard to visualize, well, I have a hard time visualizing in 4D. Maybe you don't. But what are the symmetries of it? What sort of rotations can we do? What sort of reflections can we do that is still that four-dimensional icosahedron? And then the other question is, and this is the one we're really concerned about, is what stays the same under this motion. So if I take my, my box here, we'll pretend this is the, so if I take this and I spin it around, then the top of the paper and the bottom of the paper are still the top of the paper and the bottom of the paper. So those are fixed under the spinning motion. And if I flip my paper, then this bottom edge and this top edge are still the bottom edge and the top edge. So those are fixed under the flipping motion. And so we care about which things, which faces in our objects are fixed under these different motions. And we'll get into why we care about that in a bit, but that is sort of what we care about with these symmetries. And so what we're going to do with these is we're going to make a graph of these shapes. So a graph is just a collection of dots and lines put together. And so we're going to have, for our graphs, let's just start with a line here. And we're going to make a graph out of this we're going to have one dot at the top representing the whole object itself. And then we're going to have one dot representing each vertex. And then we're going to have a grounding dot at the bottom just so it's all connected and it has a minimal point always. And then we connect them. So we'll see more examples of this, but basically we're going to have one dot for the whole object. We're going to have one dot for every edge in the object, one dot for every vertex in the object, and then we're going to connect those lines. And so later on, we get a few more definitions done. We'll look at another example of a bigger shape than a line, but that's what our graphs are. So we're looking at these graphs, and we're making algebras out of these graphs. And so algebra is not only your favorite subject in school, but it's also a mathematical object. So it's a mathematical set with operations. And so it's a collection of objects that can be added together, multiplied together, as well as we can do sort of multiply by a number. So, you know, we have x plus x is 2x, so we can write 2x down. And then the addition and multiplications have to satisfy a long list of properties, which I decided not to put on the screen for you, but it's a long list of properties that they have to satisfy. You know, like distributive property, associative property, if those words mean anything to you. So this long list, if I satisfy all of them, then I am an algebra. So for us, or so for some examples, complex numbers, so the a plus bi, the complex plane, polynomials, so, you know, just like 2x squared plus 3x plus 5, you know, set of all those polynomials, matrices, which are just arrays of numbers, you know, writing numbers across in lines. So all those things are examples of algebras. For us, the objects in our algebras are going to be the edges in the graph. And so for each one of these edges, that is going to be an object in here. And how I multiply them, I'll just call this edge 1 and maybe this one edge 2. Multiplying is just stringing them together, a concatenation, like making a word. So I could have like E1, E1, or I can just tack on an E2 to the end. And so it's like making a word, just stringing all the letters next to each other. And that's the multiplication. The addition is just taking one of those plus another one of these. So I could add like that. All right, so that is going to be our algebra. Now with our algebra, we're going to have a little caveat in there where if I can get from point A to point B, but two different routes, it doesn't matter what route I take, so we're going to call those routes the same. And so if I add a few more letters of the alphabet, or a few more subscripts there, so E1, E3 would be the same as E2, E4. So I'm going to count this. I'm not going to count this path and this path as two different paths. I'm just going to count it as one path. Just I can get from point A to point B. It doesn't matter how many different ways I could do to do that, but I can get to work from my house. So one of the questions is, well, you know, it's easy for me to sort of write this down, but you probably don't have a picture in your mind about what is this algebra, like what does it look like? We have maybe a better sense of what algebras look like in terms of, you know, we had the x-axis and y-axis and I can graph pictures on it, so we have an idea of what that looks like as an algebra, but we don't really have a picture of this. And one of the things why is we can keep on stringing these letters together infinitely many times. So I can have an infinite string. I can just write E1, 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 E1 forever. And so how do you begin to describe, well, what is the size of this algebra? Infinite isn't a really good description. And so, you know, how do we talk about this? So what we're going to do is we're going to sort of slice our algebra into pieces. And so we're going to have a bottom slice of, well, how many different, you know, ways are there to have zero edges? Well, just one. All right. How many different ways can we just have one edge? You know, so how many strings of length 1 are there? How many words of length 1 are there? How many words of length 2 are there? How many words of length 3 are there? We're going to look at each piece separately. And how many strings I need to represent it is called the dimension. So dimension in the sense of to, you know, represent where I am right now, I have to give you latitude, longitude, and altitude, and that would completely describe where I'm standing right now. And so 3 pieces of information, dimension 3. And so how many strings do I need in order to completely describe this slice of the algebra? Because, for instance, I don't need, you know, E1 and 2E1. I don't need both of those. E1 is sufficient. And so we're going to have that. All right, so that's the end of the definitions. But let's look at some examples. All right. So again, back to our line, we have this graph that we already put on the board, and then I'm going to label the vertices this time. It turns out in order to represent this slice, we don't need both of these edges coming down from V1 because of that path equivalence thing. And so I'm just going to write it based on the vertice the edge is coming down from. So V1 would mean either edge coming down from V1. I don't need both of them. All right, so what is the different slices? We already said that we have zero, or we only have one way to make zero edges. And then how many ways are there for one edge? Well, I could just have V1 or V2 or V3. So I need three different pieces of information to describe the slice one, the level one. How many for two edges? So I'm putting together two edges at a time. I could have V1 times V1, or I could have V1 times V2. But can I have V1 times V3? V1 times V2 is this path. V1 times V3 would be this path, but we said they're equal to each other, and so we don't write them both down. So this is the same thing as V1 times V3. Then I could do V2 times V1, V2 times V2, and I can list them all out, and I get 8 total. Okay, so now this is the audience participation time. How many different ways can I do 3 edges together? So I'll give you a minute. You can even talk with your friends if you would like to figure out how many pieces of information do I need to describe the level 3. So we have 8. I'll give you a hint. It's a number greater than 8 and less than 100. All right, anybody want to throw out a number? Now we've narrowed it down to between 8 and 24. So 21, very good. So we have 21 different ways. I didn't list all 21 out, but one way we can think about it is with these 8 listed up here, I can put V1 at the end of any one of them, and that doesn't violate any rule, so that's 8. I can put V2 at the end of any one of them, so that's 8 more, 16. But V3 cannot follow V1. So I cannot go on this one. I can stick it to the end of this one, but not that one. Yes, that one. Yes, that one. Not that one. Yes, that one. Yes, that one. So there's 5. I'm allowed to stick it on the end. So 8 plus 8 plus 5 is the 21. So we have 21 different ways. Now, the reason I had you think about it is because hopefully you see if I said now grading 4, you could do it, but it starts to get a little annoying perhaps, if you want to go off to any slice you want. And so we want a general way of counting this and not just keep on doing it level by level, building up like this. And so that's where generating functions come in, and that's just a fancy word for infinite polynomial. So polynomials that just keep on going forever because I can have words of any length, and so I need a number to describe any length of word. And so in our case, these coefficients of our polynomials are going to count this dimension number we're coming up with. So the one for this example is going to be 1 plus, and then 3t, and then 8t squared, for instance. And it turns out that the really cool thing is all of our generating functions for all of these shapes we're talking about and all their symmetries we're talking about are always going to have this form here of 1 minus t over 1 minus t times f of t. So this f of t is really what we need to find, okay? So how do we find it? Well, we can count paths in the graph in order to get this f of t. So I don't even have to try to think about what are all these possible allowed combinations. I just have to look at that picture I drew, and that will tell me everything I need to know. So let's do that for our example. So we want the paths of, so the powers of t are just keeping track of what the path length is. So how many paths are there of length 0? Well, 1, 2, 3, 4. There's 4 vertices. I'm starting and ending at the same spot. There's 4 places I can start and end at the same spot. How many paths are there of length 1? Well, there's 1, 2, 3, 4 paths of length 1. And the sign change here is just how many lines I use to make my path. So odd number of lines to make that path means it's a negative. And then how many paths are there of length 2? Well, I have this one, and I have this one, but remember we said those two are the same. So I'm only going to count it once because those two paths are equivalent. I just care about where am I starting and where am I ending. And so I have t squared. And so that is that polynomial that I was looking for. I factored it because it's cool how all of these shapes built up from triangles always factor into that nice form, and we'll see another example. And so plugging that into our generating function form, 1 minus t over 1 minus t times that f of t function I just found. If you use long division, then you can, divide out as many terms as you have patience for. And notice we recognize the numbers 1, 3, 8, 21. If you would have been told to do 4-dimensional, then you would get 55. And so you can keep on going on. So how do the symmetries fit in? We sort of talked about symmetries and forgot about them for a while. So how do the symmetries fit in? We can do the same thing with a symmetry of a line. So there's really only one symmetry of a line. If this is 0.1 and 0.2, I can flip it. So that's 2 and 1. And so I still have a line, but now neither vertex stayed where it was. And so I'm not going to put any of the vertices on my graph because they moved. And then I still always have the bottom. And so here's my graph for that symmetry. So how many paths of length 0? 2. How many paths of length 1? There are none this time. And then how many paths of length 2? There's 1. And I only used one line to get there, so it's going to get a negative sign this time. And so now we have that generating function for that symmetry. And so we can use these generating functions to take a look at the building blocks of an algebra, and these generating functions tell us the number of building blocks. And so there's some steps going on in here where by looking at those numbers, like the 1, 3, 8 numbers, looking at the numbers when you plug that in and use your long division, then you look at those coefficients in every line. It will tell you how many building blocks using some linear algebra. But it essentially tells you the building blocks of the algebra. So while you have the building blocks, you can say, well, this is what my algebra looks like. It looks like this building block and this building block and this building block. All right, so let's look at another example. So something a little bit more complicated than a line, but not as complicated as the 4-dimensional icosahedron. So we have a triangle, and I'll just label my vertices. And so what does the graph of this triangle look like? Well, we have one triangle. We have 3 edges. We have 3 vertices. And we have the bottom point. All right, so the triangle contains all 3 edges. We always go down to the bottom point. And then this edge here, this represents the edge 1, 2, say. So it contains both vertex 1 and vertex 2. It connects those 2 vertices. So I'm going to connect them like that. And then this one we'll say represents 1, 3. 1, 3 connects vertex 1 and vertex 3. So it goes down to vertex 1 and vertex 3. And then this edge would be the one connecting 2 and 3. Notice it looks like a cube, and that's how I draw all my cubes now. So if you use this trick, it's a really handy way to draw any dimensional cube. So you can use that the next party you're out drawing 4-dimensional cubes by just using numbers 1 through 4 instead of 1 through 3. So let's count how many paths are in here. So 1, 2, 3, 4, 5, 6, 7, 8 paths of length 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 paths of length 1. I can go 1 or 2 or 3, 4, 5, 6 paths of length 2. Remember, I don't have to care about any other way of getting there, just I can get between those 2 points. Paths of length 3, well, I can get from top to bottom. And again, all the ways of getting there are all equivalent, so just one path from top to bottom.
So is your polynomial always going to be monic?
Yeah. Mm-hmm. Yep. And another fun fact is the coefficients of your polynomial always add to plus or minus 1 as well. Yeah. It's a good check to see if you counted right or not with these bigger ones. It's like add the coefficients. It's like you get 3 and you're like, oh no, I counted wrong again. Counting is hard, it turns out. All right, if I rotate the triangle, so spin it around, then I just have the top and the bottom because none of the vertices are in the same place and none of the edges are in the same place. And so I have a situation similar to the line where I just have 2 minus t cubed. I just have one path of length 3 in there. And for reflection, if I reflect the triangle down the middle like that, then we have the triangle, the edge 2, 3, the labels might have flip-flopped, but the edge is still the bottom edge. And so that's on here still. And I'll put it in the same relative position. And vertex 1 didn't move, so that is still on here. I just use dashed lines to remind me that those are not length 1 edges, those are length 2 edges. And so here we have 4 paths of length 0, 2 paths of length 1, 2 paths of length 2, and then 1 path of length 3. And so we get the polynomial 4 minus 2t minus 2t squared plus t cubed. Notice how all of these factor into these 2 minus t to a power thing, which turns out it was really key to writing a general response for no matter what dimension you're looking at. So, and just for the fun of it, here's the building blocks that you get when you do this. So you take these generating functions, or these f of t's, plug them into the generating functions, use some long division to get the coefficients. So that first coefficient of t in that, you can solve a system of equations, so solve some equations, and you get that the building block for this algebra is 3 what we call trivial representations, 0 sign representations, and 2 standard representations. So representations of the symmetric group, exactly. So those are the building blocks that make up. And then the slice 2, the level 2, would have different building blocks. So every level has the building blocks that make it up. Okay. All right, so now the brief history. So this is a relatively new area of math. In 2002, Gelfand, Raytox, Sukonic, and Wilson were looking at pseudo-roots of non-commutative polynomials. So you know what a polynomial is, and you probably learned that you could factor polynomials, and if you wrote your answer this way, and your friend wrote their answer this way, that you both had the same answer, but in the world I live in, that's not true. Those are not equal to each other. And so what do you mean by root? What do you mean by factoring? You have all these questions. And so they were looking at this question and what do the pseudo roots look like for these things? So that's what they were studying in 2002. In 2005, they realized that this could be associated with that triangle graph I was just showing you, and that in general, you can make these graphs with a couple of constraints of how you draw your pictures, make the algebras with these paths, and it was a very interesting object to study in its own right. And then Wilson was my dissertation advisor, so in 2006 I started working with him on this. So between 2006 and 2008, that was the period I was writing my dissertation, and we looked at these symmetry graphs of these objects and found that that could be that would say the building blocks in general. So extended it to not just be the full graph, but these sort of sub-graph pictures having to do with the symmetries. And then, so the n-dimensional tetrahedra, that'd be like the triangle, the pyramid, going up from that. And then the last several years with my students have been looking at other polytopes, other shapes, and what their symmetries are, and trying to find out these f of t functions. So the main goal, what is f of t functions? Because from there, then it's just solving a system of equations to finish the problem. And so the hypercube, that's just the 4-dimensional cube. The semi-hypercube, which was really annoying because it's made up of 2 different shapes. It's made up of hypercubes and pyramids. And so it made it a little bit more complicated. And then the icosahedron, which I showed on that first slide, that three-dimensional 20-sided die picture. And then currently the 600 cell, which is the four-dimensional shape that was on the other slide as well. So one question might be, well, how do you get students involved where hopefully you're able to follow along so you can see maybe like the students could start on the same level as that. And so some ways to get students involved is they can begin the work without fully understanding representation theory. If they know how to count, they can start with this work. And so you can do a lot of these pictures just by brute force, actually drawing the picture, manually counting the paths, and then looking for the patterns with that. Another thing is that this topic actually combines the area of math of combinatorics, which is the fancy word for counting, geometry, linear algebra, computer science, algebra in general. So because it's pulling from a lot of different fields, you can start with a lot of different interest levels. So I have sometimes computer science majors working on the project who don't necessarily understand, they understand the math enough to know how to program, but they don't have as much of the math background. I usually require a linear algebra background to begin working on this project so they at least have some familiarity with these types of abstract objects, so this sort of abstract thinking. So what they have done, so they found a shortcut to find these paths. They use different counting tricks to count how many things are fixed under a symmetry with these bigger shapes. So you're talking about like 10-dimensional things, how many faces are fixed. And then use combinatorics to find the generating functions. How do we count the paths in a fast way? And then, more recently, as the shapes has gotten more complicated, using more computer programming to have a program sort of run through these possibilities and count them. So this is sort of what the students have, tools that they have used in their work on this project. And so just to give you an idea of the results that they're getting, this is the part of the talk that was required of maybe only the experts understand, or maybe just I understand. So this was for the cube. That is that f of t function. It's pretty, though. It has these 3 minus 2t terms and these 2 minus t terms. And then the next one maybe is not quite as pretty. For the semi-hypercube, remember I said it was kind of more of a pain. Well, this is 1/2 of the result. So here again, they programmed a computer to actually evaluate this whole thing. All right, so this entire sheet of different commands, different cases, and so the computer will actually throw out a number for you, so you don't have to do it all by hand. So that's for one of the two cases for the semi-hypercube. For the icosahedron, because it's just three-dimensional, we don't have to have a general formula. And so these are what they look like for the icosahedron. So just all the results, all those f of t functions. And then for the 600 cell, that's even worse than the semi-hypercube picture. And so here is just one example of a reflection of the four-dimensional icosahedron and what its function looks like. And so you can see because it's four-dimensional, we have these extra layers here, 4 dimensions, 3-dimensional faces, 2-dimensional faces, etc., and then their connections. So those are the sort of the things that they have done. So here, they did this one by hand, but our computer program tells us what things should be on each level, and then tells us the connections. So, and we'll actually count the paths for us. So they've given presentations at the Seven Rivers Undergraduate Symposium, the Joint Mathematics Meeting, which is our national meetings for math, and then Math Retreat Circa, and then my student will be talking next Friday at the MA sectional meeting here on campus. So if you want more of this, you should go to his talk at 12 something next Friday. So that is it.
Do you have ways of so you make a vector space with the basis the edges?
Right. Yes. Yeah.
And you have a way of multiplying them.
Right.
So do you have can you multiply edges with faces, or does anyone do that?
No, because it's just the graphs. You're just talking about the edges themselves only. So it's basically the free algebra on edges modded out by this, this path relation. Yeah. Mm-hmm.
Build on Michael's concept, would want to walk with the faces, that seems like it's strictly more information, and you would even build a homology theory.
But the faces in the graph, though, I mean, because remember the,
Yeah, it's not a graph anymore. Now it's some kind of little thing that you would take the homology of. So,
yeah,
well,
I guess.
complex.
I mean, yeah, I mean, I'm not sure what information that would give you then, so we could think about what additional information that would give. Because you don't need the you know, the homology to tell this graded dimension that we're looking at. So.
Does this have to do with the 11?
No, it does not. That's a different research project.
Okay.
I have a sign on my bulletin board outside my office, like why 11, because it's a different research project my student and I were working on a few years ago. 11 was the abnormal case. Like every other case worked the same except for 11, and that's normally not the abnormal case in math, normally it's like 2 or 3, so it was annoying. We never figured out why that was the abnormal case. Okay.
So I know it's not a requirement, but is there, are there like practical applications from this?
I mean, the original question of looking at pseudo-roots came from a physics application standpoint. You know, there's other people currently working on these types of algebras that are looking at the word causal, which is kind of a fun word to say, but not a fun word to try to define. And so, you know, you can look at these other properties of these algebras. So then it sort of has some physics type, you know, like string theory type applications. Yeah. But I don't do that side of it. So some of the students I've recruited from my linear algebra classes. I teach that one quite frequently, so the top students in those classes. Other times, like we send out a department email at the beginning of fall semester saying who wants to do research and give a description of all the projects. So some students have approached me like, hey, that project sounds interesting, and I talk to them about, you know, their background and their interest. So. Chris?
So I'm wondering about functoriality properties of this thing. So if you start with some complex that you build and include it into a larger complex, do these graphs have relationships with each other? Do the symmetries have any relationships with each other?
I mean, I haven't thought about like the functor relationships, but like these symmetry graphs are all sub-algebras of the main algebra. And there's some duality properties that we have with these as well. So.